All right, well then we can go on to arginine. Let's try to draw the side chain for that. I guess that's the pirate's favorite amino acid.
So that's why, okay, that's why this will be the first deprotonate, because any value higher, like still the lowest value, like 2.3 or something,
Right.
will only deprotonate that.
That's right.
Okay. That's what I don't understand. So in terms of the text, so it's connected to this carbon, which has 2 hydrogens coming off of it, and then it's connected to another CH2, which is connected to another. Like, how does it really look?
Okay. In the table, they used condensed notation here.
Right,
now, what we have here is 3 CH2 groups. And then that's attached to an NH. And we're asking exactly what does the structure of this carbon look like?
Yes.
Looks like this.
Got it. Okay. That's
When in condensed notation, when we say CH2, what we mean is a carbon that's bonded to those 2 hydrogens.
okay. Yeah, my misconception was that the 2 CH2 groups were somehow connected to the carbon. Okay. Cool.
So this is notation here indicates 3 CH2 groups in a row. 3 CH2 groups in a row like this. It would be very easy here, I think, to accidentally add or drop carbons. You always want to make sure that you count the carbons in your side chain. Especially, it would be easy to miscount the number of carbons if you start thinking that this is part of the side chain. It's very easy to start thinking this carbon is part of the side chain. That's why you should always label the alpha carbon, so we don't start thinking that that is part of the side chain.
Okay, and which nitrogen is being protonated there? Because it's basic. Right?
Yeah. How do we know it's basic? Because they have that little C in the column. Now, what type of functional group is this over here? Well, I don't even know what the name of this is. It's, yeah, I have no idea. In some ways it looks a little bit like an amide, but it's clearly not an amide. There must be some name for this that I haven't memorized.
It's kind of like an amine. So there's a double bond.
Something like an imine, that's right. So an imine would be this. So it looks like kind of a hybrid of an imine and an amide. I'm sure in some book there's a name for this, but we don't need to know the name. But even without the name, we should be able to predict the reactivity. Now the question is, who is the basic nitrogen? This one, or this one? And we definitely should be able to answer that using the skills we've already worked on earlier today. For example, earlier we learned how to tell why amine nitrogens are basic and amide nitrogens are not basic. We can use the same skills to figure out which of these nitrogens is basic. That's something that would be best to do on paper. What's the skill that we need? Drawing resonance structures. We used resonance structures to explain which nitrogens are basic and which are not. So let's try drawing another important resonance structure from this picture. That's looking good. This is very similar to the types of resonance structures that we drew. when we were explaining the amides. So I think this is the resonance structure that both of you drew. And therefore, is this the basic nitrogen? Yeah, because it has this negative charge. So this nitrogen here with this negative charge is eager to gain a proton and quench that negative charge.
And to even prove more, you can do the resonance from the other nitrogen, correct?
That's an excellent point. That's right. There's another resonance structure where this lone pair moves over, and that would give us another reason there's a negative charge up here. That's very similar to what we have over here as well. So that's right. There's another resonance structure where this lone pair moves over, and then we get this negative charge. Both of those resonance structures indicate these two nitrogens are not basic, but this nitrogen is basic. What makes something a good base or a good nucleophile is a negative charge. After all, we know our classic base is hydroxide. And part of what makes hydroxide a good base is the negative charge. So if there's a resonance structure where something has a negative charge, that tends to indicate that that would be basic.
We can equate basic nucleophilic.
Basic and nucleophile have subtle differences, but they're very similar. Okay. That's right. So oftentimes, things that are good bases are also good nucleophiles.
And that's
in particular,
because for both of them, the negative charge.
That's right. After all, we know a nucleophile is somebody who donates electrons. And remember, the Lewis base definition of a base is somebody who donates electrons. So there are some subtle differences between nucleophiles and bases, but that's not going to be our top priority to review right now. The key thing is that negative charges make things into both good nucleophiles generally and good bases. However, sometimes somebody who doesn't seem to have negative charge really does because of resonance structure. Now this is something I might have mentioned before. This would be a very good test question to give you a molecule you've never seen before and explain which are the basic atoms in it. Almost no student gets that right because, as I might have mentioned to you before, I've almost never seen a student draw a resonance structure unless the problem had the word resonance in it. Students almost never think about resonance unless the problem talks about resonance. Well, at this point in the course, we should be looking for resonance. We should be looking for resonance to help us explain the patterns that we're seeing, even if the problem never mentioned it. We've just seen how resonance is very helpful because it shows us that there could be charges in places you didn't think. So this nitrogen up here would be the basic nitrogen, all right? So if we're at a very low pH, what form should this take? Which nitrogen should we put the proton on? This nitrogen here. So at a very low pH, this would be the form of, what's this called? Arginine? This would be the form of arginine.
Again, we see NH2 plus here opposed to NH3 plus. It's kind of different.
That's right. Because this already had 2 bonds to a carbon, whereas this nitrogen only had 1 bond to a carbon. So yeah, every single one of these amino acids takes a little while to understand the details. That whole kind of a little story. That makes sense for arginine?
Yeah.
Okay. You might want to make a note then in your version of the table about which nitrogen is the basic nitrogen, but you should also make a note that you should be able to explain why that's the basic one if necessary. All right, so now let's try drawing tryptophan. So here's the beta carbon. Sorry?
I was just thinking of the resonance or aromaticity, but I think that's a real issue for histidine.
Right. Now, why is this nitrogen not basic? It has a lone pair. I think the best way to think about that here, now there are plenty of other resonance structures where this has positive charges. Maybe we won't draw them, but we can draw other resonance structures. We could say move these electrons over here, like this. You could do this, say, that would leave a positive charge on the nitrogen.